the equilibrium constant, which depends on the temperature. And last class we have found that the Ka will be the formula is pretty straightforward. If you have reaction, so we found ln Ka T2 by Ka T1, which is delta H SS1 by R into 1 by T1 minus 1 by T. Okay. So we this is actually for the heat of reaction, constant of reaction. Okay. Or this you can say that the particular temperature range heat of reaction doesn't change, very small, which will not be likely. So in the heat of reaction, the function of temperature, we have a separate formula, which is R ln Ka T by Ka T0, which is the reference temperature, T0 to T delta H Rxn, this is 1 T prime T prime square. And heat of reaction at T0, that is standard state, 25 degrees centigrade, 298.15 Kelvin, where the heat of reaction is known. And once a particular temperature heat of reaction is known, we can find out other temperature. Okay. So what we have essentially learned about this guy, which is the equilibrium constant K, and Ka means in terms of the activity, and activity has been defined in last class. And very important part is how the K is varying in temperature. This is very important. It is not generally given in the books. You can get, or you can get K T0. Estimation of K T0 can be done. I will discuss how you can estimate K T0. Once you estimate K T0, and once it is known, then you can calculate K T, a particular temperature. And how to estimate K T0, that we will also discuss. Okay, because we have seen in the last class. So there are some specific formula for the Ka to estimate, which is, so how to estimate Ka T0, which is you can actually have the formula Ka exponential, which is minus delta G SS1 by RT. So you can actually have this as T0, delta G SS1 if you can calculate. Okay, so basically at T0, all the properties will be available. Heat of formation, heat of reaction, gives to energy, everything is after T0, standard state. And from that, so this will give you the fit. This will give you the estimation of KT. Once KT has been estimated, then heat of reaction, all those things we have discussed last class, and I demonstrated the problem. We can actually get this integral evaluated, KT0 is known, and eventually we can calculate the KT. So that's the essential, that's the kind of thing which we have learned. So equilibrium, so chemical reaction equilibrium, it actually is comprising of the equilibrium constant. Okay. And so estimation of heat of reaction is very important. Without that, we cannot proceed further. And estimation of heat of reaction is done by Hess's law. Estimation of heat of reaction. Estimation of heat of reaction, delta H Rxn SS1. Okay, so what SS law says? If the stoichiometric reaction for reaction 1 can be obtained by algebraic operations, the multiplication or addition or subtraction, or the stoichiometric equations for reaction 2, 3. Then the heat of reaction can be obtained by performing the same operation on the heats of reaction where the heat of reactions are actually known. So that means, I will give you a simple example. For example, we have 2C plus 3H2, C2H6. Okay? We have to find out heat of reaction for this. And generally in the books, any of the books you take, that Paris Chemical Engineering Handbook, if I want to know heat of reaction, there are thousands of reactions, heat of reactions are given, but you won't get for this reaction. So unfortunate. Then how to get heat of reaction for this? Generally speaking, heat of reactions are given in the handbooks for the formation reaction. What is formation reaction? C plus O2, CO2. That one from the elemental constituents. So the elemental constituents, you get a material that is called formation reaction. So most of the cases, the heat of reaction will be given for the formation reaction even at 25 degrees centigrade. Even at 25 degrees centigrade. So other temperature also it is very difficult to get. So for this, to estimate the heat of reaction, I have the three reactions which data actually given. I note it down. R1, which is C2H6 plus 7 by 2 O2, which is giving 2CO2 plus 3H2O, and delta H reaction T0 R1 T0 is given as minus 1539.8 joule per kilojoule per kilomole per mole, kilojoule per mole. Reaction 2, C plus O2 CO2 delta H R1 reaction T0, which is minus 319.5 kilojoule per mole. Reaction 3, H2 plus half O2 is given as H2O delta HR3, which is R1 R2 R3, reaction T0, which is given as minus 285.8 kilojoule per mole. These are the data given. The formation reaction, this type of reaction is known as, is not formation. What kind of reaction it is? Any idea? Combustion reaction. So generally the data of the table, the heat of, it is either given in terms of heat of formation reaction or the combustion reaction. So Hess's law says that from this information you have to get the heat of reaction for this. So the question is how to do algebraic manipulation to get this reaction. How to do algebraic manipulation to do this reaction? If I say this is my reaction R4, so R4 should be equals to R4 equals to 2R2, 3R3, 2R4, 2R2 plus 3R3 correct? Minus R1. Hess's law says that the heat of reaction should follow the same way. That's the Hess's law. So whatever algebraic manipulation you are doing to obtain this reaction, stoichiometric reaction, Hess's law should be having the same kind of algebraic operation. That means the delta H reaction of R4 will be 2 into delta H reaction of R2 plus 3 into delta H reaction of R3 minus delta H reaction of R1. That's Hess's law, very simple. So based on Hess's law, what we do get? Delta H reaction R4, delta H R4 reaction T0, which will be which will be minus 104. No. Is 1559. I'm sorry. 1559. I'm sorry. 1559 for day. We can have modified answer. Quick. Yes. Kilojoule per mole. See, this unit of heat of reaction has a lot of controversy. If you look at, it has 1 mole, it has 7 by 2 mole. Then which is referring? Per mole of C2H6 or per mole of oxygen? 1 mole of CO2, you are saying? No, it's 1 mole of C2H6. 1 mole of C2H6. Similarly, it refers 1 mole of carbon or 1 mole of oxygen, no problem. But it is referring 1 mole of hydrogen, not 1 oxygen because half. So 1 mole of hydrogen is reacted to half mole of oxygen. So this, all the books have this controversy. Nobody is giving the right answer. What is this mole? Question mark. Everybody is giving this answer, this thing, and we actually do the calculation and solve it. But if you look at the basic stoichiometry is a very difficult subject. If you look at the basic stoichiometry and looking at the units, I am very much concerned about the units. You look at the units, you can find out this is not that straightforward. So you have to be very careful and do the calculation. Okay, so we have learned the Hess's law, and one thing actually we can we'll find out from here. If we do further calculations, the Hess's law and heat of formation. It is not a heat of formation here. This could be heat of formation. This could be heat of combustion reaction. So, based on Hess's law, one can also conclude. Based on Hess's law, one can conclude delta H Rj reaction number Rx and T0, which could be summation I equals to 1 to C nu I delta H I 0. Okay, which could be summation products mod nu I delta H I Fi 0 minus reactants delta HFI 0. So now you can see that what we are doing actually, this actually makes sense. So this thing actually already we have discussed. Delta H reactions, actually we talked about the heat of in the stoichiometry. We have done that. We have taken a reaction AA plus BB going to CC plus D. I was talking about delta H reaction. Okay, it will be what? It will be C of heat of formation plus D of heat of formation of B minus A of heat of formation minus B of heat of formation. Okay. The question is, if B is already in molecular constituent, we don't take heat of formation, it is already there. What I am talking about is 25 degrees centigrade. If it is other temperature, I will come back. What I am doing actually, this means this 0 is very important, 25 degrees centigrade. 0 is very important, 25 degrees centigrade. Now 25 degrees centigrade, so I am assuming that none of these constituents at its molecular state, but elementary state. If it is elementary state, that should not come. That means the heat of reaction will be, for this case, at 25 degrees centigrade, C minus C in heat of formation of capital C plus B of heat of formation of B minus A of heat of formation of A minus B of heat of formation of B, provided none of the components are at the elemental level. If it is elemental level, then we should not consider that. That will be ignored. Understood? Very important. This is not basic stoichiometry. You have to know basic stoichiometry for doing chemical reaction equilibrium. Was all those things covered in chemical reaction equilibrium? These things are not covered? Okay. Yes, so let's verify this. I want to verify this. That heat of reaction can be obtained from the heat of formation. Heat of reaction can be obtained from the heat of formation, and that can be justified by the same Hess's law arguments, same kind of algebraic manipulation. Whatever algebraic manipulation you will do to obtain the chemical reaction, same algebraic manipulation can be obtained from the heat of formation reactants. Let's start with that. Okay. So, I will give the example problem. Previous example was not the based on heat of formation, it was combustion and formation reaction. Now we do the purely the formation reaction. So my main reaction is C5H12L plus 8O2 gas phase plus 5CO2 gas phase plus 6H2O L liquid phase. I want to obtain the heat of reaction based on formation reaction. So formation reaction should be for this, for this, for this, not for this. This is already elemental. Okay. So let's talk about the first reaction, formation of C5H12, and how to get formation reaction. What will be the equation? Let's see. We have done chemical reaction engineering. We should be quick enough. Fill in the blanks. This right side is L. Left side. Left side. 5CS plus 6H2. This is given as delta H R1 reaction at T0, 25 degrees centigrade, given as minus 173 kilojoule per mole. Okay. This could be per mole of C5H12. Again, I am saying this unit is a very controversial. You cannot say per mole of carbon, per mole of hydrogen, per mole of C5H12. Okay. These no books address that. When I was teaching the process calculations, I was giving the states on that. This per mole is very important. Generally, don't care. We do the calculation, solve, and do that thing. If per mole is not there, if mole is supplied, and you have to say that heat of reaction net, not in terms of per mole, you have to be very, very careful. If you are not careful, you will be doing mistake. Generally, you don't need it. But if you set up, I am giving the mole number, you have to get to the entire. That means that if you talk about the, for example, the first law of thermodynamics. What is first law of thermodynamics? Remember that, right? Q minus W equals to delta E or delta U. And Q actually sometimes you see this should be indicated in the heat of reaction. So you need to have net enthalpy change here. You cannot put per mole. Then you have to be very careful and it's coupled with the first law of thermodynamics. I am not doing it here in the class. So these are the fundamental things you have to know. Next, R2. This is done. CO2. We need to have formation reaction for this, which is, right, this way, CO2G, which is C plus O2G or CS plus O2G, which delta H R2 reaction, heat of reaction is given minus 393.5 kilojoule per mole. It was given already in the last example problem. R3 is of course the remaining one. H2L, H2G plus half O2G is giving H2OL, which is delta H R3 reaction T0, which is minus 25.84 kilojoule per mole. R4 we have to obtain. The same Mason's law we apply. What is the algebraic manipulation to obtain output? What's the algebraic manipulation to obtain output? Algebraic manipulation to obtain output. R4 equals to algebraic manipulation for R4. R4 equals to 5R2 plus 6R3 minus R1. So delta H of reaction, delta H reaction R4 T0 can be obtained as 5 delta H reaction of R2 plus 6 delta H reaction of R3 minus delta H reaction of R1. Okay, and these are actually formation. So what I am saying that 5 delta HF0 of CO2 plus 6 delta HF0 formation of H2O minus delta HF0 of C5H12. Now look at the stoichiometric coefficient. So what I said before in the very beginning, the heat of reaction is 5 of heat of formation plus 6 of heat of formation minus heat of formation of C5H12. This is not counted. So this is now proved. So heat of reaction formula is based on this summation, this concept. This concept already I have discussed in the last class. This has been now proved by Mrs. Law. One nice clear? Okay. Okay, so now we have done all this drama at temperature T0. Now temperature is not T0. Of course, temperature cannot be T0. It will be different temperature. How to calculate heat of reaction at any other temperature? The temperature is not T0. Okay, so let's work on that part. So effect of temperature. Effect of temperature on the standard enthalpy change. The standard enthalpy change of a reaction. Standard enthalpy change of a reaction. Okay. So we need to have three-step process. To know more of the heat of reaction, please consult the book by, there is a book, Elementary Process Calculation by Felder and Rousseau. Have you read that book? Felder and Rousseau's book. And there it was very nicely explained. Some of you might not have heard about that book, right? How many of you didn't hear about that book? Felder and Rousseau? It's quite a lot. What's about Manikandan? You have not heard, but you are not raising the hand. I said, how many of you have not heard about Felder and Rousseau? Yeah, that's why if I don't catch you, won't even many of you actually. It is good that you have not heard. Even when I did my BTech, I didn't hear about that book. And that book, one beauty is the process calculation of the boring subjects. In fact, I never liked that subject. In fact, after reading the course, after having that course, I was all the time cursing myself why I have chosen chemical engineering, such a boring subject. Because I was taught from the book Himmelblau, or there's a called Haugen-Warson Rajaj, Haugen-Warson. So Haugen-Warson are the most boring books of the process calculation, and next comes Himmelblau. And there are a lot of books like Bart and Bora and all those books, right? Yeah. So those books already I have the copy. So when I joined IIT Madras, I was given the course to teach. I was telling that, there's a course I hated much. So then I took this course as challenge, process calculation, which course I actually really got bad grade in my BTech level, and that course was given to me to teach. And my job was to make it most interesting course. So I taught that course in vector space, in terms of vector space, and in fact I introduced the range space and null space there. And I found that course is one of the most interesting courses in chemical engineering. But I don't think you have been taught with the range space, null space and vector space with that course. In fact, that you have seen that bypass, purging and all those things, recycling ratio, all those things. There are multiple units in the component, and chemical process calculation get very complicated. How to solve with bypass, purging and all. There is something called degree of freedom concept. The same degree of freedom what I told in the class, the same degree of freedom, similar kind of concept will be there. The same degree of freedom concept we can easily solve. In fact, some of the things we have learned in engineering mechanics called free body diagram. So the mixture of the concept of degree of freedom and the free body diagram, we can easily solve automatically any of the complicated process calculation problem. Okay? So this is the beauty of, if you know mathematics, if you know the mathematical logic, any subjects will become too easy. But the only thing is you have to appreciate the mathematics. Okay, so three-step process for that. So reactant in standard state, reactant in standard state at T. Okay, this is my situation. I want to calculate the heat of reaction at temperature T. Step 1. T I cannot do anything. I have to cool it down to T0. On only T0 I can get all the property. T0 plane I can do the property, estimation, everything, then go back to T. Okay. So T0, step 1, cooling. And here I do reactants in standard state. Reactants in standard state at say 298.15 Kelvin. Step 2. So when I get the reactant at 298.15, I can happily have the reaction. If I have the reaction, by SS law I can calculate the heat of reaction at T0. Then I have to come to T. 3 steps. First to get T0. At T0 do the reaction, do whatever you want. Come back to T. 3 steps. Okay? Step 2. So reaction at 298.15 K, we call delta H 298 degree Kelvin. You get products at T0. Products at T0 you will get. And then you will get, so you have step 3, heating step, products at T. And that's what we wanted. Reactant from T to product at T. At temperature T, reaction going on T to T. I cannot go straight to do a calculation. I have to go by this step. This step is okay. We have heat of reaction. This step requires the specific heat. This step requires the specific heat. This means what? I am having a sensible heat change. Cp delta T. This is also Cp delta T, heat of reaction. So, what actually happens in that heat of reaction for this step? We will be having the 3 terms. One is the heat of reaction term at T0 and 2 terms comprising the Cp's. Clear? So, this is the way, this is the most rational way one can actually do the calculation. So, let us have the mathematical prelude of this step 1, step 2 and step 3. So step 1, which is delta HR0, which is T to 298.15, the Cp dt. So it will be summation reactant nu I Cp Ig dt. Remember that 25 degrees centigrade, we will assume that is a standard state and Ig. The Cp Ig is valid. That I told you, right? The Cp Ig formula, what is given, which is A plus Bt plus Ct square plus Dt cube plus Dt to the power minus 2. It is at 25 degrees centigrade. Okay, and it's changing around that. So I'm assuming that with that, this A, B, C, D, these things will be changing with respect to 25 degrees centigrade. That's why the integration is 298. So this is a cooling step. So initial condition is T, final step is 298.18. Heating step is 298.15 to T. The third step. So step 2. Step 2 is very easy, you know that. Heat of reaction. That is delta H SS1 Rxn T0, which is summation I equals to 1 to C mu I delta H HF0. That we have already done. This is very trivial one. Third step, delta H products, which is 298.15 to T summation products gamma I Cp Ig. So what will be delta H reaction? Delta H reaction T, which is delta H reaction T0 plus what will you get? Integral T0 to T. Okay, and you can see now minus n will be coming here. So you will be having summation I equals to 1 to C nu gamma I Cp Ig T prime dt prime. I think this thing I have discussed earlier. Last class, if you look at last class note, delta H Rxn SS1 T is given as delta H Rxn SS1 T0, and this was given in terms of A delta T delta A T minus T0 and so on. This was done in the last class. I am looking in other perspective from SS1. So this is the way everything is actually being calculated here. So, and delta H RX1 T, everything is done. So any problem if we can give, we can actually solve for that. Okay, so let's take a real life problem. Okay, everything is done. I think we have done enough of the heat of reaction. Let's look at the equilibrium constant for one of the equilibrium constant problems and see how to proceed. So the question is, estimate the equilibrium constant. Estimate the equilibrium constant. This question is not there in the assignment, so please write down. Estimate the equilibrium constant Ka at 1000 degree Kelvin. At 1000 degree Kelvin and 0.1 megapascal. Estimate the equilibrium constant Ka at 1000 degree Kelvin and 0.1 megapascal for the reaction. For the reaction, which is CO2 gas phase plus hydrogen gas phase, CO gas phase, H2O gas phase. Okay. So what's the formula for this? What's the formula? Which formula we have to start with? They wanted the equilibrium constant at temperature 1000 degree Kelvin, pressure 0.1 megapascal. What's the formula? I have not discussed Bantam's. I have to discuss some equation. I don't remember our Bantam's equation or not. I know some equation. Ln, what is that?
Ln K by K T1 equal to H by R 1 by T1.
But sir, delta H is not constant, no?
Delta H is right.
So,
Rln K T2 by K.
Rln Ka T by Ka T0, which is integral T delta H reaction SS1 T prime square. Okay. Two things you have to do. I have told on in the class. This thing and this entire integral. How to get K T0? K T0 formula is known. It's the exponential of minus delta T SS1 T0 by R0. Right? So K T0, which is exponential minus delta G SS1 T0 by R0. So how to calculate delta G SS1 T0 is you can use the Hess's law. G SS1 T0 by Hess's law. Only thing is I have to supply the formation reaction, otherwise you cannot calculate. So let's have the formation reaction data. Let's have the formation reaction data. So C S plus O2G R1, which is CO2G delta HF0 CO2G is 3 minus 393.978 kilojoule per mole. Delta GF0 CO2G free energy change is also given minus 394.815 kilojoule per mole. R2, which is CS. You can see that we need to have formation reaction for this and this. This is always already at elementary level. It's already at elementary level. Formation reaction for this, so only need to have three reactions. Three formation reactions. CS plus half O2G, which is COG, and for that reaction we have delta HFCO G, which is minus 110.4 532 kilojoule per mole, and delta GF0 COG, which is minus 137.327 kilojoule per mole. Part 3 is H2G plus half O2G, which is H2OG, which is giving delta HF0 H2OG, which is minus 341.997 kilojoule per mole, and delta GF0 H2OG, which is minus 228.600 kilojoule per mole. Okay. So all data are given. So now we have to calculate K80. First to calculate G delta GSS1 is, which can be done by Hess's law. We have the stoichiometric coefficients. We have the formation reactions. So based on formation reaction, it is possible to calculate delta GSS1 T0. How much you are getting? Delta GSS1 T0. How much you are getting? For the elementary substance, heat of formation is 0, and heat of weak speed energy change is also 0. For example, hydrogen. The same way. Formation in the substance elementary level already, the heat of reaction, heat of formation, and free energy for the formation goes to 0. With that, how much you can get? K8T0. First delta GSS1. For first we get delta GSS1, then we will go for K8T0. Yes, how much? 28. Delta GSS1, how much you got? 28 point? No units, right? You don't tell any units. That's what I'm saying. At the end of that class, so many 55 lectures are over and we cannot tell the units. Kilojoule per mole. 28.888 kilojoule per mole. K8 is 0. K8 is 0. Put proper values of the R, otherwise you won't get wrong, you won't get correct result. Put the units properly here. Give the proper units, kilojoule per mole. This is Kelvin. This will be what? R unit will be 3.4 what? Dimensionless, huh? That's what I'm saying. This is the problem with you guys. You just put the numbers. If you put the numbers, you won't feel the subject. Then the units are what? Otherwise there is no point. Otherwise there is no point. You have to give the units. Without units, you cannot tell the values. How much you are getting? I am asking for K8, so everything is known. You have to just enter the value and get the answer. Provided units are consistent. Unit has to be consistent. 8.685 minus 6. The unit will be there? Okay. There's no unit here. 8.685 10 to the power minus 6. Okay. So this, now we'll be going for this term. Delta H reaction SS1 T prime. So what is that formula? Delta H reaction. Delta H reaction SS1T. I hope you have taken all this data. delta H reaction SS1 T. What's the formula? Delta H reaction T. What's the formula? What formula will apply? So formula is delta H reaction SS1 T0 plus delta A T minus T0 plus delta B T square by 2 T naught square by 2 plus delta C T cube by 3 minus T naught cube by 3 plus delta D T to the power 4 by T naught to the power 4 by 4 plus minus delta E 1 by T minus 1 by T0. Now I will give you ABC. Components CO2G, COG, H2OG, H2G. A, B into 10 to the power 3, C into 10 to the power 6, D into 10 to the power 9, E into 10 to the power minus 5. 45.369, 28.068, 28.850, 27.012, 8.688, 4.631, 12.055, 3.509. No values are reported here. Minus 9.619, minus 0.258, minus 1.006, 0.690. The validity of temperature range is given 2000 to 3000 degree Kelvin. So you can actually, so this, when this formula is given, CPIT formula, this validity of temperature, it is also reported, and the reporting temperature range is 2000 to 3000 degree Kelvin. That means with that kind of variation you can actually happily apply this formula. Okay, so now you can calculate, you can tell me what are delta A, delta B, delta C equals to 0, delta D equals to 0, and what are delta E? Quick. Delta A. Delta A. Delta A, how much is coming? Remember that here the stoichiometric coefficient is all 1. If they are multiplied by stoichiometric coefficient, calculation may be difficult. Not difficult, you have to properly take care of the stoichiometric coefficient. Delta A formula was given in the last class. What's the formula of delta A? Anybody can get, tell me, delta A formula? Summation you are not saying. Summation gamma A. Minus 15.463. Minus 15.463. Delta B. Delta B. 9.0. How much is delta B is coming? 8.08. No. 4.9. Who said 4.489? 4.489 is into minus 3. 4.489. Minus 3 is there, no? This being reduced by 3. delta E 10 to the power minus 5 will be, plus 5 will be there. Delta E should be having 10 to the power plus 5. How much is delta E? How much is delta E? Delta E pardon?
7.66
How much you got? 9.045. It should be the calculation step. I tell you minus 0.258 plus 1.006 plus 9.619 minus 0.690. It should come 9.677 10 to the power 5. It should come 9.677 10 to the power 5. Okay, next step is, so this part is actually done. So all these calculations we have got, and T is known, T0 is known, so you can get this part happily. Okay. So T0 is known, so we can actually have to integrate. We cannot put T here. It's a function of temperature. And delta H Rx1 SS1 T0 is actually obtained. How to obtain? How much is delta H Rx1 T0? With the data already. How much delta H Rx1 reaction of SS1 of T0? How much you got? Minus. No way. Delta H reaction at T0. Delta H reaction at T0. How much you got? No way. It should be plus. So delta H Rx1 is should be 41.449 kilojoule per mole. Okay. And then once everything is known, then you have to get the expression here, divide by T prime square T square, and then integrate. Okay. You can do integration analytically, no problem. You have the integration, you can do analytical integration for this, and we get this right hand side. This term is already known. You should be putting here. R is known. It should be 1 by R. If you take anti-log, you will get the Ka at temperature. So I want to know the answer next class. So next, I think we will be meeting again on Friday. And then Friday we will be talking about the homogeneous gas-phase reactions, many other problems, how the equilibrium constant will be varied with different other properties.